Hi everyone. Today what we're going to do is we're going to change gears a little bit. And so we've just spent an entire kind of segment working on an awful lot of algebra. We're dealing with some rotation angles and getting into some angle identities. And what we want to do now is we want to change gears and start to look at our trigonometric ratios now as functions. So what you'll see on the very top is we're going to work our way through and we're going to go and graph y equals sine x. So I've put on the red and the blue just maybe some background stuff from the ways that maybe you have thought about your sine curve from last year. So hopefully we're good that sine x is equal to opposite over hypotenuse and that you view your trig curve, your sine curve, in that regard. Specifically, if we can get to the point where we view our sine curve as what is happening to our opposite side, I think that can become really useful. Some people are going to have what we have in blue, which is working our way through and using XYR definitions as their background. And so maybe your focus is what's happening to the y coordinate. Either of those cases are good. You're going to hear me talk specifically about the opposite side using our SOHCAHTOA definitions. So what you see then in the next instruction is to go through and complete the following table. So I've given you the table, and really what that is a table of values. I've turned it on its side so that we can fit in a little more space. What we're going to do is we're going to work our way through our angles in radians of multiples of pi by 6. And so what I'd like you to do is to be able to work your way through and come up with the exact values of those. So to help us get started, if we were to calculate the exact value of sine 0 in the first column, well, the sine of 0, when I have an angle of 0, my opposite side is 0. If you were then to calculate what the sine of pi by 6 is, I'm hoping that we're good for that value to be a half. And if you had to calculate the sine of pi by 3, then we should have an exact value of root 3 over 2, and so on and so on. So what I'd like you to do now, pause the video and work your way through filling in the exact value in that table. Okay, we should be back. And so, hopefully, as we continue the rotation around our set of axes, our terminal arm, working up to one full rotation, we were able to correctly go through and come up with the exact value of every single one of those ratios. This should give you a little confirmation that what we did in the last chunk of lessons you have down. Now, what we're going to end up doing is graphing these, and so for the purpose of graphing, having some decimal approximations can be helpful. So, to fill in that decimal approximates, that shouldn't be an issue, since the only one of these values that you don't know a decimal for should be the root 3 over 2. And so, pretty quickly on your calculator, you can punch in what root 3 divided by 2 is, but we should get approximately 0.87. And so if we can fill in those values, then we should come to a table of values that looks like this. So when we look at the instructions then on the next part of the page, we're going to use the decimal values of sine x to plot our points, x, and the value of sine x on that grid. And so I'm just going to slide up our screen, and we should be good to be able to go through and plot all of those points. So what I'd like you to do now, pause, complete plotting all of those points on your own. Pause it now. Okay, we should be back, and you should get a little confirmation then that we have all of these points on our graph. Now, as we go through and we examine these points, I want us to get really, really good. And my guess is that most of us have a pretty decent idea of what our sine curve already looked like from grade 11. And so we knew that our curve would rise up from 0 and then come down and then follow the same pattern but on the other side. I was a little off on that last one. I'm going to adjust my point a little bit, and there we go. So we should have something that looks like that on our grid. What I'd like to do before we get to that next instruction is I'd like to break down that grid. Because the more we can have that sine curve memorized, and the more that we can understand it, is going to help us when we get into problem-solving situations. So the first thing I'd like to highlight is when we went from 0 up to pi by 2, notice that on your rotation angle, that represents quadrant 1. And I just want you to imagine what's happening to the opposite side as we rotate from an angle measurement of 0 to an angle measurement of pi by 2. We should see that our opposite side begins at 0 and then gets longer, and hits a maximum when we get to pi by 2. We then notice our next interval, and that interval is going to go all the way to pi. There's our quadrant 2. And so what's happening to the opposite side as we progress through quadrant 2? Well, your opposite side gets a little bit shorter, until we eventually have no opposite side at pi. We can then see the next intervals. Well, the only thing that changes as we move into the next interval, which is quadrant 3, is that my opposite side is negative. So at pi, I have 0 opposite side. Then my opposite side gets a little bit larger, and that is the largest it could be when we get to 3 pi by 2. There's our quadrant 3. We can finish off our rotation as we rotate through quadrant 4. My opposite side then starts to get a little shorter, and eventually disappear. If we can think about our sine curve as the movement between our 0 to our max, to our 0 to our min, to our 0, and notice that all of those changes occur at an axis, then I think you guys have got your sine curve down pat. Now, this also affords another opportunity for us to discuss, okay, why do we start to work our way through radians? As we work our way through, I just want you to notice that that sine curve is really stretched based on my decision to use my scale of 0.2. So what we're going to come back to a little bit is going to be the why did we bother with radians anyway question that a lot of us would have had when we got introduced to them. Okay, let's finish off the last part of this instruction then. We're going to focus in on continuing our graph back to negative 2 pi. If we focus in on our zeros, our maxes, our zeros, our mins, then we can pretty quickly say, well, pi by 2 backwards is going to then have to get me to a min. Another pi by 2 backwards to that gets me to my 0. Another pi by 2 back gets me to my max, and another pi by 2 back gets me to my 0. My bet is you could probably draw a pretty decent sine curve, knowing what the shape looks like, using just those 5 points. So if I was to go through then and say I'm going to connect those with a nice smooth curve, curving down that whole direction and then curving up that whole direction, that's not a bad looking sine curve for our purposes. So let's make sure that we know where the zeros, the maximums, and the minimums lie on a sine curve, and we should be good. Okay, what we're going to do now is go through a complete review of our cos graph. So, what I'd like you to do is to jump to that cos curve on your lesson page, and I want you to go through the exact same process. Fill in the table of values, plot your points on the given grid. And so, I want you to pause the video now and give it a shot. Okay, we should be back, and we should have a table that looks like that on our page. Now, with that table, we have the ability to go through and deal with our graph. And so I can go through the exact same process of plotting my 1, my 0.87, my 0.5, my 0, my negative 0.5, my negative 0.87, and so on our grid. As we do that, we should get to something that looks like that, which then can be connected with a smooth curve. And to pick up the pace a little bit, we can see our quadrants on that graph as well. From 0 up to pi by 2, there's our quadrant 1. And when we deal with cos is our adjacent side. And so if you were to ask yourself, what's happening to your adjacent side in quadrant 1? Well, if my terminal arm is straight across, then my adjacent side is as long as what it could be, so a length of 1. And as soon as my terminal arm begins to rotate, my adjacent side gets shorter, until we get to pi by 2. And when my terminal arm is vertical, I have no adjacent side, so a value of 0. If we then flip over and we rotate just past pi by 2, well, all of a sudden, I have an adjacent side again. The only adjustment is that I'm on the left, so now my adjacent side is negative. My adjacent side gets a little bit longer, and eventually gets as long as it can when I get to the end of quadrant 2 at an angle value of pi. Right away again then, my adjacent side is going to start to get smaller and start to get smaller until I have no adjacent side when I get completely vertical at 3 pi by 2. And as soon as I cross 3 pi by 2, I now get another adjacent side, I get another adjacent side, and I'm back to having the longest adjacent side I could have when I get back to 2 pi. Thinking about your cos curve in its quadrants is going to be super useful. Again, working our way through maximums, zeros, and minimums will help us. So, very quickly then, we should be able to do the same thing with extending that curve backwards to negative 2 pi. I know that pi by 2 back, I have to get to a 0. Pi by 2 back, I have to get to a minimum. Pi by 2 back, I get to a 0. Pi by 2 back, I get to a max. And when I connect them all with a smooth curve, curving down, that one got really bubbly. I don't like that one. That a soft curve and down. I like that one a little bit better. Now I begin curving up, and now I continue curving down, and I get to something like that, which isn't too shabby. So that should be a nice quick review for us, and maybe an opportunity to look at our sine and our cos curves a little bit differently from last year. Okay, what we're going to jump into now is something that I will assume is brand new for all of us. We're going to deal with our tan curve. So, as we take a look at the screen in front of us, you'll notice that we go back to our basic definition of what tan is. It's opposite over adjacent. That's going to make our tan graph a little different because our tan curve does not include the hypotenuse. There is no hypotenuse. And since the hypotenuse is always determined as the longest side, That means that when I create my tan graph, I'm not as fixed as what I used to be. We'll see that as we work our way through. So as you begin to think about your tan curve, you're trying to think about, well, how does the opposite side compare to the adjacent side? We may go back to XYR definitions. So let's go slowly and let's build it up through our table. So I'm hoping that we don't have to draw diagrams for these, that we are able to work our way through. That as we look and we try to determine the exact value of tan 0, that you can view your terminal arm as being directly across. And so when I calculate the opposite side over the adjacent side, since I have no opposite side, I have 0 divided by, I get to 0. As I then work my way through and determine my pi by 6, my small angle, I'm going to have a small opposite side over a large adjacent side. I'm going to get a small value. You can then calculate the tan of pi by 6, and we should be good that that is 1 over root 3. As you start to progress to now have tan of pi by 3, I have a bigger angle. So now my opposite side is going to be larger than my adjacent side. I'm going to get a value that's going to be bigger than 1. Now, I'm just going to write down root 3 because we don't need to write root 3 over 1, and we should be good. We work our way through. We calculate the tan of pi by 2. I am vertical, so when I calculate opposite over adjacent, I have no adjacent side. I am dividing by 0. That's undefined. I'm just going to put a bar or a cross through that box. I get no value there. I then jump in to quadrant 2. My 2 pi by 3 is going to give me a big opposite side over a small adjacent. But I know that the adjustment that gets made is since I'm in quadrant 2, my adjacent side is negative now. I get a negative root 3. I work my way through to the next, and we should be able to pick up the pace, eventually getting to the tan of pi and 0. As I work my way into the third quadrant, now my opposite and my adjacent sides are the same sign. That means my value is positive. So for my small angle, I get 1 over root 3. For my large angle, I get root 3. And when I get completely vertical again, I have no adjacent side. It's undefined. I work my way through into 5 pi by 3. My opposite side is really big compared to my adjacent. But because I'm in quadrant 4 now, my opposite side is negative. So my tan ratio is negative. I work my way through to my 11 pi by 6. Eventually getting back to 2 pi. So we work our way through in that instance, and there is us coming up with exact values. Now what we can do is go ahead and replace all of those with decimal approximates. Well, in this case, we may have a few things to come up with approximates for. And so if we push some buttons and we get a decimal approximate for 1 over root 3, we're going to get approximately equal to 0.58. Now we work our way through and get a decimal approximate for root 3, and we're going to get about 1.73. We notice that those values pop up over and over again. They just maybe change to a negative value depending on what quadrant we're in our rotation. And so as we go through and we complete that table, we now have a table of values for our tan value, tan ratio. Okay, as we take a look at the page in front of you, the next question I've asked you are there any interesting values? And I would like us just to make a note right here that we notice that at pi by 2 and 3 pi by 2, we get an undefined value. Now, that is something that is new for us, and we have not encountered that on a trig curve before. Let's come back to maybe why it's interesting, or whether you consider it interesting, in a moment. But what I'd like to do is to go ahead and now graph those blue approximates. So you'll notice the scale on our grid is changed. On our y-axis, each scale or each axis line is equal to 0.5. So there's your scale. Let's go ahead and plot some points. So as I work my way through, 0, I had 0. At pi by 6, I've got approximately 0.58, so I'm just a little bit past 0.5. Pi by 3, I get 1.6, so almost 1 3/4. I'm not sure, I can't plot anything at pi by 2. When I then get, and keep going, now I'm down at negative 1.73. I'm a little bit past 0.5, my 0, and now I see that pattern repeat. And there are our plotted points. Now, if I was to ask you to go ahead and connect those, I think we may face some difficulty. That for us to connect our sine and our cos with a smooth curve, we could kind of see how those things would connect. But all I can really see to connect right now would be to connect those points and those points and those points. I don't really see a logical way for us to be able to connect them. And I definitely know that I can't do this, because we found that at pi by 2, it's undefined. We do not have a point there. So I have to make sure that I can't connect those in the green. I'm a little unsure what to deal with. Okay. One of the things that I'd like to come back to is what's happening with your tan curve. Now, I think this may be a little bit easier for us to deal with if we were to take our calculator right now and turn it back into degree mode. Because what I'd like you to punch into your calculator is something that gets very, very close to that first interesting value, pi by 2. So pi by 2 is 90 degrees. Let's punch in something like 89 degrees to see, like, what is the value at 89 degrees for tan. And so if we punch in tan of 89, you're going to notice that the tan of 89 degrees is 57.3 approximately. That's huge. And so if we were supposed to get really, really close to tan, or to pi by 2, we're going to eventually have to plot a point that would exist where 89 degrees and 57.3 exists. So let's go back a little bit. What if I was to ask you to calculate what the tan of 80 degrees was? You're going to see that you get approximately 5.67. That seems more manageable. And so if I was to be just a little bit to the left of pi by 2, I would have a point up here somewhere that would exist at 5.67. We would then be able to connect these 2 points pretty logically, and maybe we can see what is going to happen. Keep in mind that when you calculated the tan of pi by 2, it was undefined for a reason. That if you were to calculate the tan of pi by 2, we could come up with a value that looked like this. And I'm hoping that we remember from way back in Unit 2 what happens when we have a non-zero on top divided by a 0. When a fully reduced fraction is a non-zero divided by 0, we have an asymptote. And maybe you can see then why we would have an asymptote at pi by 2. Notice in the green portion of that curve, we can see that our curve is going to increase really, really fast. We can see from the tan of 89 that it's going to take off. But I can never get a value for the tan of pi by 2 because it's undefined. And so, just to be able to get rid of that ugly green, that we have the ability to then connect and extend up towards that asymptote. Pretty quickly then we can draw the conclusion that when I'm vertical again, that being at 3 pi by 2, I have another asymptote, and therefore I would approach and approach the same way as we go, and there is your tan curve. I want you to notice it's going to look considerably different than what your sine or your cos could. I also want you to notice a couple key things as we go. Notice that I have arrows going up and down in both directions on that tan curve. My tan curve has no maximum or minimum values. Now, that should make sense a little bit if we draw back on what was discussed at the beginning. There is no hypotenuse in my tan ratio. And so since there's no hypotenuse, then there's no guarantee of what number's on top or what number's on the bottom. Now, I'm going to draw some really ugly diagrams here. But it is possible for you to have a very, very steep right triangle because there is no requirement for the way the opposite side must compare to the adjacent side. My opposite side could continue to grow and grow and grow, while my adjacent side remains very small. And so my tan ratio has no max. You want to see that? Then punch into your calculator the tan of like 89.9999999 and just see how big your tan ratio can be. So there is your tan curve, and that is what we need to drill into our heads. Now, for us to be able to work our way through, there's a couple key features that I want us to address to kind of draw back for us. The first thing that we should know is that when we jump in and we deal with our tan curve, you're going to notice a couple other things. If you had to calculate the period of your tan curve, your period is pi. Notice that for both your sine curve and your cos curve, your period was 2 pi. It takes a full rotation to repeat, where your tan graph only needs a half of a rotation to repeat. Secondly, we should be good that the amplitude on both your sine and your cos graph is 1, because we know our amplitude is half of our height. You take a look at your tan graph. Your tan graph has no, and these should be a colon, it has no amplitude. It can't have an amplitude because there is no top or there's no bottom. We can't calculate the height of our tan graph. So if we were to go through and we were to go and extend this back to negative 2 pi, here's what I would do if I were you. I know that my curve is going to do this wavy thing. Okay, it's going to give me a wavy thing. Well, what do I know about that wavy thing? I know every pi units, anytime my rotation arm is vertical, I'm going to get an asymptote. So if I were to rotate back to negative pi by 2, my rotation arm is vertical. That means it's an asymptote. But also I notice that I am pi units apart from my previous asymptote. Well, then I know that another pi units, or the next time my rotation arm is vertical, At 3 pi by 2, I have another asymptote. Okay, what are the key points that I need to know for my tan graph? Well, I need to know where the zeros are. And my tan is 0 anytime my rotation arm is horizontal. Now I do that wavy thing. Well, what's going to define the shape of the wavy thing? And we actually use different points. What we end up using to determine the shape are our multiples of pi by 4. Because if I asked you to calculate what is the tan of pi by 4, very quickly you should be able to give me 1. Pi by 4 is my diagonal on my square. My opposite side is the same as my adjacent side. And so to use that, then I know if I go backwards, my pi by 4 would give me a value of -1. I'd be in the fourth quadrant. I know then that a pi by 4 on either side of those zeros, halfway between the axes, is going to give me a 1. It just might be a +1 or a -1. And now that I go back into the first quadrant, I'm positive. If you have those points, then you're going to get a pretty good shape on your tan curve. Because now you just graph the wavy thing. I want you to look at this middle interval for a second, because I also want to add in the other feature. Everywhere to the left of that 0, your tan curve is curving down. As soon as we hit that 0, your curve changes to curving up. And by just having those 3 points on your grid, you can get a pretty decent looking tan graph. And there we go. We added in a lot of new stuff. So your job is to know your sine and your cos curve, which you have from last year, and now get to know your tan graph just as well. Okay, we're going to jump to a second video for today to talk about some general statements and where we're going to go next with these functions.